All right, so we're going to do a little review of data structures, then we'll implement a linked list and a binary search tree as a review. Okay, so when we talk about data structures are important because they're a way for us to organize our data in a special way that works with our memory, with our computer memory. So to properly be able to visualize data structures, you kind of need to understand how a computer works. So computer has a CPU and it also has RAM. So these are the units in our computer that typically are used when we are running a program. So our CPU knows where its current location is pointing at. So basically the next empty memory or where it's, so the current location is where it is like executing, or what's the next available thing, and it can read or write to that location that it has access to, and it can do basic operations like math and logic. When we are running our program, our actual data, like when we're setting variables, we're holding on to strings, we're holding on to lists, these are all being held in the RAM, in the random access memory. So if you're buying a computer, you're typically hearing of RAM and versus memory. So RAM is for when the computer is executing programs. This is memory that is randomly accessed, so it could find like empty slots to use. The actual memory that is usually like in terabytes or something like that. So the RAM is usually, like you see, 8 GB RAM, 16 GB RAM. It's usually smaller. That's for like quick access. The actual storage of the computer is typically like in like 500 gigabytes or a terabyte or something like. So it's bigger storage. It's typically slower to get information out of there. So programs are using RAM, the random access memory, to store information pretty much. So RAM is just a list of addresses pretty much. It's just a sequence of memory slots basically, and each of these slots can have a value. So like here, this example, at this address, we have a value of 4. Let's say that is a variable, an integer that we held onto. Addresses, this address through this address is holding on to a string called hello. And this string is an array or a list, so it is sequential. It holds on to things one right after the other. And so yeah, memory addresses can hold on to numbers, can hold on to letters, but it could also hold on to pointers. So a pointer or a reference, which is we've talked about it quite a bit. A reference is just the memory address of another location. So if your program, like let's say this reference in your program is called like node. So when you say like node equals this new node, and hold on to the reference of that address, basically when you're accessing that the memory address of node, it gives you or like root, if we were going to do like root of the tree or something like that, it holds on to the address of that new root node, and so when we want to access it, it goes into here, and then it sees, oh, my actual data is at this address, so I'm going to go to this address, and that's where my node information is going to be held, where you can find like the value and stuff like that. So it's sequential. In this computer diagram, each spot, so each spot of the here is 8 bits long. So I won't get too much into bits and bytes, but basically each bit can hold a value. So like think of like 0, 1, 0 and 1, these are binary bits. And different types of values have different sizes. So if I see size of int is 4 bytes. What if I want size of a pointer? Size of a pointer is going to be 8 bytes. Size of a character. Size of a character is 1 byte. So basically your computer organizes everything into like little bits and bytes. And the reason why arrays are helpful is because you just have a solid chunk of your memory that is taken up. So our array points to basically the first address, the first element. And everything after that we can access with the index, because it'll basically take the starting point and then add 3 times the size of whatever you're trying to access. So if I want to access index 3 in this array, so this is 0, 1, 2, and 3, it'll start off at this first point. It will add 3 times the size of whatever is being held in there. So if it's a character, then let's say 1 byte. So 3 times 1 byte, that means it's going to go from this address, go down 3 bytes. So it'll increment. So in binary, this is 1, this is 2, this is 3. So it'll keep going down and add more. So 1 plus 3 equals 4. This is the address for 4, and it'll access the memory at that address, the value at that address. Yeah, so arrays are great at having constant access time, so O of 1, but a big problem is that they have to be continuous. They have to be 1 block. So in memory, because it's accessing things at different times and creating different pieces of memory, it ends up using like a big chunk of memory for this list, let's say, and then there's some space here, and then it uses like another bit because of how like the memory is chunked up in like internally. So there's a lot of times where you end up with like little bits of spaces between the used up space that is just kind of wasted. So
Zeta.
Yeah.
It turns out I don't have to have that conflict anymore, so I can teach this if you want. Just because I know it's easier to teach one's own material. I don't want you to have to do this in real time.
Sure. Yeah, definitely.
Cool. So I'm gonna, if you stop sharing your screen, I'll start sharing my screen and just start teaching the same thing.
Sounds good. Thank you.
Hey everybody. So this, oh, right, I'm not sharing my screen yet, or am I?
You are.
I am. Okay, cool. So you guys can see this is the same thing as before. Sorry to, I mean, I think I'm just going to repeat the first 10 minutes because I missed some of it because I was on a call. But yeah, basically I wanted to first introduce this idea, which might seem like a lot, but it's sort of the essence of what a computer is. And it helps a lot with understanding arrays and especially linked lists, because linked lists are kind of a response to how arrays work. And arrays are not a response, they're sort of a natural implication of how a computer actually works. And so without this part of it, it can be confusing why things are done one way versus another. So yeah, basically a computer in its essence, forget about the hard drive or the monitor or the keyboard or the mouse or anything like that, besides for the CPU and the memory, which we're going to call the RAM. So in this case, we're saying it's an 8-bit computer. And what that means is that each one of these memory addresses is 8 bits long, and each one, and each like instruction the CPU takes is 8-bit long. I don't even really get to that part, but the basic idea is that we're going to have this sort of like scroll of memory, and we're going to index it. So, I just decided everything's going to fit in exactly 1 byte. We'll just pretend that's the case. Everything fits in 1 byte. But the idea is you have these bytes one after another, and they all have some kind of memory inside of it. And all the CPU can do is read what's at a memory address, then maybe do some operation it's capable of, like addition or subtraction, or telling whether something is true and false. So basic arithmetic and logic can be handled by the CPU based on what it reads, and then it can write to a specific memory address. And then importantly, it always knows where it is. And that way it could just jump to another memory address depending on what it reads or wants to do. And this is how everything that works. This is how it jumps from one part of your program to another. And it's how it can jump around a data structure or something along those lines. And then the only thing I wanted to point out here that is important is that right here we have a memory address, and its value it's holding is a different memory address. So that is what we mean when we talk about a pointer or a reference. It's just that when we look at this memory address, like let's say we have the value, like if I were to have, if I were to have, I know it's here, where's the letters? Okay. If I were to have the letter X in my program, like a variable associated with this memory address, then when I access X, it's going to point here. And then I can follow what is here over here, and then I see the value. So when something looks like x.next, the idea is that x.next actually has to live somewhere in memory. This is the address of x.next, but this is the value of x.next, and the value of x.next just points to something else. So in this case, we just have the letter O, but this could be where the location lives that points to the next thing in your linked list. And then this is what happens when you follow it. You get that thing in the linked list, which is probably another node. So I hope this idea helps clear things up. And before moving on to arrays, I'm assuming I have until like 9 to do this, Zainab?
Yeah.
All right. So, or sorry, I even meant 9 at my end. So that would be 10 at your end. Okay. So does anyone have questions? And you should have questions because this is brand new. Does anyone have questions about how a computer works?
So just kind of linking back this concept with data structures. So is that kind of why we have linked lists versus arrays, where it looks like it does the same thing, but a linked list can actually be jumping around versus an array, which has to be one contiguous block of memory?
Exactly. Yeah. So that's what this whole lecture is getting towards. So as you can see, if I go all the way down here, I start talking about linked lists, but a linked list doesn't really make sense until you see this, which is sort of the biggest downside to an array, which has to be in order, which requires you to know how an array works. And an array is basically just the data structure that memory actually is, which is just stuff in order, but a specific slice of it. So we can spend more time here if people want. I think it's good to ask questions about stuff that's like this, because there's no way this isn't introducing 10 new ideas in your mind. So ask away. Like this is new material.
I had a quick question about arrays and how they work in memory. So since it's all contiguous, do arrays essentially just need to point to the start of the contiguous list, and that's how it just accesses, like, oh, at 0 and then whatever +3 for the index and stuff like that?
Exactly. Yeah. So that's a really good point. Array will point, like if you were to look at the value of some element array you had, not array brackets 0, but rather just array, it's going to, if you were to print that out on, or in a language like C, you'd be able to see, oh, this is a specific spot in memory. An array just points to that specific spot in memory. And then the nature of the indexing is that it does this sort of multiplication, which if you say array 0, it's going to say, okay, my starting point, which is what array equals, plus 3, plus, in this case, the index, so 0, times how big each one of those elements is. So in the case of a character, it's just 1 bit, 1 byte. So array at index 0 is going to get you what exists at that first index. Whereas array at 3 is going to be able to instantly jump to 3 because it knows starting point plus 3 times the size of the character. And if this was some other thing, like if we were to have this side by side, and let's say instead of a character, we had something represented by something larger, like it's a little hard to think about it in those terms, like what is larger than a byte. But let's just say we say, okay, all of our numbers are represented by 4 bytes. So in that case, it's sort of like we'd go to that first element, and that first element would be a 4, but that first element doesn't just take up one thing, it takes up the next 4 things. Or 0, 1, 2, 3, right? That 4 exists in this whole space, and it's only after that we start seeing our, 5. To move that up slightly, but basically each one of these things is going to take up a block, but the array knows where it starts and it knows how big each thing in it is. And because a classical array can't have different types of things in it, it always knows what to multiply just to jump to that second, third, 80th value. And note that if we try to start mixing things where I said like, okay, well, I have an A, and that is, it's a little hard to work with these. If I had an A and I said, okay, that A takes up just, the first element, and then I have a 5 and it takes up the next 4 bytes, that now this doesn't work anymore. This thing of saying like jump to the second element or something. Well, I can't do that arithmetic anymore because I can't guarantee that the size of each thing is the same. And how Python solves that, I don't know.
That was going to be my follow-up question on how Python just lets you put different kinds of data.
Yeah, exactly. Well, I know a little bit about how like the V8 engine in Chrome does it for JavaScript, and it's pretty nuts because this is the problem using a high-level language, that if you start digging into the details, what you find out is when you make an array in JavaScript, behind the scenes, JavaScript is making a lot of decisions saying like, well, what is in this array? So how do we represent it? Because if you do make, just an array of numbers in JavaScript, JavaScript will guess, oh, I think we can just represent this as an actual array of integers, and then we'll see. And then if suddenly you add an A to that, it goes, we can't do that anymore. Now we got to create something new, maybe some kind of like, dictionary type thing, because that is one way of handling the fact that your values might be different, but your keys could all be the same or something. So yeah, it's not totally straightforward, but that's a weird thing about data structures, is bringing you back to what it looked like in the 50s or something, and then what it looks like today is so advanced because they just packed all these ideas together, and you don't have to think about how it's done. It's just you have this sort of super powerful array, a super powerful dictionary.
Do pointers themselves only contain the same amount of memory to store them? So would it be possible to just have like an array of pointers that then?
Yeah, basically you got it. That's the main answer to most of these things, as in, let's say we were on a 32-bit computer. Part of what that means is that every memory address is going to be 32 bits. And as a result, every pointer is going to be 32 bits or whatever, 4 bytes or something. So if every pointer is 4 bytes, that means that you can have an array of pointers and that you're going to be able to index. And then it's just one more step to follow that pointer to what it points at. So yeah, that's the actual most straightforward solution. Cool. So any more questions about just this general idea of memory model? Even if binary is unfamiliar, we can talk about that, because I feel like some of these ideas we haven't discussed, and they do come up and sort of help to understand larger ideas. Okay, well, if that is the case, I'm going to move on. So just to reiterate, we have the basic idea of how a computer works, which I'm loving Excalidraw for this. And then the basic idea of an array, which is that, you just have your data based on its size, sequentially oriented in a list, and that list, or that array rather, starts at a specific memory address. And this is also a point in which, like in Python, it's going to yell at you if you go out of the, if you try and access an array element that shouldn't exist yet, right? If you have an array of 4 elements and you try and get the 5th element, Python is going to give you like an out of bounds error, right? So that is a cool feature of Python, and it helps a lot, but that's not fundamental to how arrays work. Arrays just point at a memory address, and then you can do what you want from there, which is one of the reasons why people don't want to use a language like C for a lot of things, because in C, it's trivially easy for someone with a pointer to just say, okay, I want to go 100 ahead of that and just write what I want there. And that can be extremely dangerous. And that's what like 85% of computer system hacks boil down to. The fact that when you have full access, you can just jump around the memory, read, write, do whatever you want. There's really no rules once you get a certain level of access, because it's just literally a bookshelf with individual books that you can pull out, assuming there's, you're not forced by an operating system just to be like, oh, I can't pull that book out because it's not me, I don't own it. But yeah, so this is the important point to start thinking about a linked list, because we saw that with arrays, they already have this great feature that you have constant time access to the one you want, because you can just index into it, and that's always going to just be solving a little math problem. The big problem with arrays is that, let's say your computer has like, let's say your computer has like 100 gigs of memory on it total, and you want to save, or like you're currently using like 80 of those gigs, and then you want to save a DVD or a movie. It's 5 gigs big. Seems like you should be able to put it there, right? Because your computer has 20 gigs of free space, should be able to put 5 gigs down. The problem is that you might have a situation like this, where this is what we would call fragmentation. So if you've ever seen that tool on your computer, like defragmentation wizard or something, its job is basically to move the blocks around to make more contiguous space. Because the problem we have here is that we used a bunch of random space, and maybe we used some space and then deleted some space, but it left us in this situation where we do have, let's say, 20 gigabytes of space left, but we don't have anywhere with 5 gigabytes of contiguous back-to-back space. And that makes sense, because the bigger the thing you're trying to save, how rare is it going to be that you have that much free space, right? So you could think of it as like, let's say an encyclopedia was not, let's say we're trying to put an encyclopedia on a bookshelf, and the bookshelf had room for, if you were able to cut up the encyclopedia. But this is an encyclopedia that going from A to Z is one gigantic book, right? So you're going to have to find this like solid, gigantic chunk of space in your shelf where you could put that encyclopedia. But someone might have the thought, well, what if our encyclopedia, instead of being one big book, it was like, let's say 26 books, where each, or even more, but each book basically represented like a part of the alphabet or something. And the books had a meaningful sequence to them, but in such a way that we can put the A section of the encyclopedia in one spot. And then just like, let's say there's a note at the back that says, hey, B comes after A. And so once you finish the A book and you see that note, you say, okay, now I'm looking for the B book. So this assumes you don't really know that much about your data, but basically imagine if you split up your giant book so that each individual book had the data you wanted. And then on the last page, it had a reference to tell you where to look next for your next piece of data. And that's exactly what a linked list is. So with a linked list, when you say like, you know, when you create that linked list class or something, which I guess we can see it side by side. Like what's, I can just make it in the scratch pad. So can you guys see that my code as well right now? Okay, so I don't want to make this too big, but if I make that class linked list, right? The first thing it's doing is, and it takes self, right? I always get confused. The first thing it's going to do is just have some kind of like, oh, right, it's going to point at a node. So do I even want to make, I guess what we're calling, we'll just call it an LL node. And we say that each node has two things, a value, which is what we passed in, and then a next, which I'm going to originally set to none. And then if down here I were to say LL node, my linked list. Okay. So based on what we have here, when I make a new linked list, the first thing is that if I were to look at my linked list, it is a memory address. So it's like this memory address here, and it has two things in it. It has a value, which I didn't pass it. That's a good point. So it has a value like 4. And then it's going to have this next value, but that currently equals none. And then the nature of the linked list is that I'm going to take this, you know, I'm sort of going to, maybe I'm going to make like, it's sort of like I'll take, like does, we'll explain this more in a second, but it's sort of like I'm going to take my linked list. Or let me draw a little more here where what this initially looks like when this comes back is like this, right? Where my linked list points to that memory address. That memory address has two things in it. In this case, a number. And then the next bit of memory is going to be its next value. But because I said it was none, this is going to be just zeros here. Because the 0th memory address is never used. It's there to represent none, or in some languages, what we call null. It's there to represent a memory address that is not meaningful, so that if you then try to do something with that memory address, it would be an error. And then the way this is going to work is that I might create a new node. So I'll call this next node equals LL node 5. And once again, I just created a new linked list, or sorry, I created a new linked list node. In this case, I'm calling it next node. And let's say it has a slightly different memory address. So it's going to be like somewhere else in memory, whatever. And this one equals 5. And again, it's pointing to nothing. And then the next step is that I'm going to take that original thing, which I called my linked list, and I'm going to say dot next equals next node. And what that means is that I'm going to overwrite this to be this. Oops. I'm going to overwrite that area, and now it equals this. And the benefit of that is that they now link to each other. So when I follow this, I have access to 4, but then I can say next, and it's going to jump somewhere else in memory, and I have access to 5 and whatever its next is. So that's sort of what happens here, where like if I were to add some arrows, it's kind of like this points, this next will point to this entire piece of memory. And then once again, this next will point to this entire piece of memory. And that's what a linked list is. Like, we don't know necessarily where it is in the memory. We just know that we have this tiny little piece of memory, and part of its data is to link to another piece of memory. But as you could probably already see, that probably presents some problems in that we no longer can do that indexing thing. So instead of having constant time access, if we want to see the last element, we actually have to start at the first and then go dot next, dot next, dot next, dot next until we hit an element whose dot next is, none. And then we know we're at the last element. So you can already see how, because of this different structure, how it actually lives in memory, we're going to have different guarantees. I just wanted to show here that when you generally don't write those memory addresses, you just sort of use these arrows to represent that. So if someone were to represent this visually, they would say like, okay, well, I have a 4, and then it points to this node with a 5, which points to a node with a 6, which points to, and then when you want to say points to nothing or points to null, you use this symbol to say that's where it ends. So before we get into the whole adding to a linked list, which we've explained a little bit about, anything we want to discuss in this section?
Really quick with the array, you said that's O1 just because you're doing the little math calculation to get to each index? Okay, just making sure I'm clear.
Yeah, and the reason why that's constant time is because you already know your starting point, and you know that every element has the same size, and you can quickly query that with size, of the type. And then this whole equation, you're going to run that one time. So most computers can do that in one step, but even if it took the computer like 10 steps, if multiplying out and adding, this whole equation took 10 steps every time, that's still constant time. As in, your array could be 10 billion, have a length of 10 billion, and maybe each one of those spots in the array, has size of like, 1,000 bytes, because it represents like a high quality image or something. But that doesn't matter for jumping right to the piece of data you want. Whereas that would matter a ton in the linked list approach. Okay, any more linked list questions? The next thing we're going to do, just to give you a heads up, we're going to talk about how one adds to a linked list. And then we're going to do a real world lead code example, which should probably demonstrate how understanding the data structure is sort of just a starting point. And then the lead code problem will force you to use the data structure in a way that shows you understand it or not. Okay, so just to recreate our logic a little bit, I have this this linked list here, which I'm calling linked list node, and it takes a value and a next. And so we already have this situation where I'm creating a new linked list, or, it seems like, yeah, so we could do it a slightly different way where I have something like class linked list, which linked list takes nothing. It just has this dot head equals none. Like you could, or sorry, self, you could split this up a little if you wanted, in such a way that I could say something like, my linked list is going to be equal to a linked list, and that takes nothing. And then all I know is that my linked list has something called head. And then to give it a meaningful starting point, like, right, so that might be what I do. So like the first thing I might want to do is say something like def append, right? Which append will add something to the end of your linked list. Well, the first thing I do is say something like, if self.head equals none. I could also say if not self.head, some people find that more or less confusing, but I'm saying if self.head has a nothing value, which the only meaningful nothing value it can have is none, then I know that I don't even have a list right now. Maybe I did and I deleted everything, but for right now I don't even have head pointing at anything. So in that case, I'll just say self.head equals linked list node, and append would have been given a value. So we just pass that value down, and that's going to return us something with a value and with a next equal to none, which is what we want, because like that's, so our situation we start with looks like this, where our head points to nothing. And then by the end of this first append, our head points to something.
So I have a question then.
Yes.
What the benefit of having those in two different classes is, like, why bother having a linked list class? Why not just call linked list node and send it the value and initiate that first one from the get-go?
Yeah, basically those are two different approaches, both perfectly reasonable. As in, what is a linked list? Well, you could say a linked list is a thing that has these various functions or these various methods on it and always has a head, and that head is going to point to the first element. And then you could say that because of that, a linked list node doesn't have any functions on it. It just has value and next. Alternatively, though, I could just say, a linked list is just me pointing at that first node. So my linked list could equal, linked list node 4. And then from there, I would know that, my linked list has access to, like, I would then put my functions on here, like append. I mean, what you're saying makes a lot of sense, and is perhaps smarter, because much like with a tree, a linked list could be represented by, like, if I point to this value 4, to this, node 4 here, this is a linked list. But if I were to suddenly point to 12, well, 12 is also a linked list. I can't seem to do that, but like 12 and on is also a linked list. So a linked list is any linked list node that points to a linked list. So yeah, let's do it that way, actually, where I'm not even gonna say, I'm not even gonna create this linked list node class. We're just gonna say my linked list equals linked list, and that's how we, we don't even have a head and next. We'll just, yeah, basically my linked list now represents the head. Something I like to do, this is a pattern that we didn't show you guys, but it's what I was taught. It's a good pattern, and it helps you see how there's not a one size fits all for this stuff. You can very much make it how you like. So I like to use what's called a sentinel node. So the idea is that internally we could have this idea of, can you have a class inside of a class? Zainab, do you know? Can you define a class with a class?
Yes.
I think you can, yeah.
Okay, cool. So I'm just going to create this internal class called linked list node. All right, you don't need those. I'm just going to create an internal class called linked list node, and it's going to have our, maybe we'll put it at the bottom even, because we don't want to have to think about it necessarily, but it's part of our class, so it doesn't live outside. And a linked list node is going to have a value and a next, and let's just call it node, because it lives internally. This is the only person who knows about it. And we'll have a self.value equals value, and a self.next equals next. Well, I guess it should just be none by default. And then for when I init a linked list, I'm going to say something like, I'm going to make a node. Does it know about node? No, you got to put that at top.
I think you just have to do self.node.
You sure? Okay, let's try that.
Hopefully.
Okay, good point. So I'm going to make a node here, because this is an internal class I have access to. And when I make a node, I have to give it a value. So I'll give it a value that represents like nothing, like none. And then this is going to return me what we call the sentinel node. So we always have access to self.head. And then when we append, so basically, I don't know if this is a better approach to you, but this way of doing it means that basically we always have at least, you know, when we're dealing with my linked list is going to point to, I guess this isn't necessarily better than what I was doing before, but
Well, I guess my question is why bother have the head at all, right? Have your init right there be value and next.
yeah.
When you create the class linked list, pass a value, and your variable that is your head, and there's no reason to have a head at all.
Yeah, there's a point there.
I guess my question is there a reason to have a head at all? Because
well, the reason is because if I do append on something, it has to know what the head is. So if I do my linked list is a linked list with 4, then I did just create a new node and it points nowhere. And then if I then say my linked list dot append 5, the assumption then is that self represents the current node, which is meaningful. You're right. Like I don't need to know the head because I'm always going to start at the head, if that makes sense. So if I don't have to say anything here, I just have to say.
you just say self.next is
Exactly right. When I initially append, if I see that there is no self.next, then I'll just say self.next equals a new link, or right, if I see there is no self.next, then I'll say self.value equals value, otherwise self.next equals, and then self.next will equal, yeah, it's kind of confusing me. I mean, yeah, no, I could just, you're right, I could just say if there is no self.next, initially just give it a value, or no, I did that already here. So if I'm trying to append a new thing, I already have my value in my next, you're right. So what I want to say is, I mean, this is good because I part of this is that we're going to get to a point where I say, well, do I even need this special logic for the first one? But so when I'm appending, I'm going to say, okay, well, first things first, I know I have to create a new node. So I'll make something called new node, and it's equal to a linked list, and it's going to have that new value of 5. And this returns me essentially a node with that value with its next pointing to nothing. And then right after that, I could say if, you know, I'm at the head and the head has a next that is and the head has a next that is none, then I just say self.next equals the new node. And basically, I just want to show that this is going to work for the sake of my linked list. So I should I want to print my linked list, and then I'm going to print it again after we append 5, and I just want to see it. So if I had that, you know, string function, I could say something like I would basically want to iterate through it. So I'm going to have something like maybe I'll have
You can probably do like current equals self to start off with the initial node.
sure, yeah, right, exactly. So I could say current equals self, and then while, which we're going to see in a second that this is the approach for doing it in general. But I'm going to say while current, which is just going to say while current is something and not none.
Well, current.next, right?
I think I might just want to say current to begin with, because let's say, I do still want to print my first value. Let's say I just had a first value. That first value is going to have a value, but its next will be none. So if I say while current.next, it's going to completely skip over that. Whereas I think what I want to say is while current, it'll look at the current node, and then at the end of that, I'll say current equals current.next. But
that makes
for
sense.
right here, I'll say something like, and I kind of want to print this all on one line. So I'll say lines to print is an array. And so I'll say while current lines to print dot append current dot value. Maybe I'll just call it values. And once current.next is none, that's going to end. So that should give us a list of all our values. And then I'll be able to write something like maybe just well, values is already an array, so we'll just print it as an array. I'll just be able to say return values, and it should be able to print that. Let's try that. I am trying to print it. Maybe I have to say string values. Try it out again. Still see nothing. Didn't.
I think you're doing code in the terminal.
New code.
Command.
Oh,
Yeah,
yeah.
you're not calling Python.
That's
Yeah,
definitely a
just
big
do
part
code.
of it. Great. So we see that our list looks like 4, and then it looks like 4 or 5. That's good enough for me. Just
Can
wanna
I
make
show
sure.
you, can I show you a way to print out the values on the same line?
Sure.
Instead of, yeah, so on line 17, you can do print current dot value.
So like that, print.
And then put a comma after the value, and there's an attribute called end. So you can do end equals, and you could just put a comma or something like that, or a space. So instead of ending each print line with a new line, it will end it with a space, and then the next print will happen after the space.
Cool. And in fact, I would love to do this, that while it's almost like I'm going to print the first one. I wonder if I print, like basically if I put an arrow here,
Yeah.
I wonder what that looks like. Oh, I kind of like that. So basically this is what a linked list is. It's a 4 pointing to nothing, or a 4 pointing to 5 pointing to nothing. Not exactly nothing, but close enough. Okay, so given what I have now, the question is, how do I add additional elements to the linked list? So we kind of just did some of that with our stringification stuff, but walking through this append, let's say I already have a 5 in there, and now I want to add a 6 to there. How might I do that? So I'm going to walk into my linked list, or sorry, we're going to walk into my linked list .append, and it's getting a 6. And then I'm going to create a new node with that 6. So that is like here. The first thing I do, you know, I made it an 8 here, but the idea is the first thing we do is create this new node, and that new node is freestanding, as in where we have a value or a variable new node pointing to that node, and that node has a value and then a next of nothing. And the idea is once we create it, it's our job to fit it in somewhere. So where do we want to fit it in our array if we're appending?
At the end.
At the end, right? So the nature of just this append operation is we want to put it in at the end. And we can do that, but you can kind of see how, like, if you like, imagine you were asked to not append, but rather insert it at like the second spot. We'd have a similar problem where essentially we have to get to the second spot. We have to sort of detach, you know, it's almost like, let's say we wanted to put it right here between the 12 and the 6. Well, our head points here. So we have a current pointer, and it's going to point first to the 4. And then it's going to point to the 12 when we say that's not the right one yet, next. And now we know we're here. So we'll say, well, what is next thing? we might say something like, well, the next of the thing that we want to make sure we don't lose track of is here. So we're just going to give that a name and give it a name like rest of it. And then we would detach this to make it point at our new thing called an 8. And then we would make it so that 8 now points at 6. And so that's how you would add something just arbitrarily in the middle of a linked list. But in this case, we don't want to just add it, you know, in a specific spot in the middle. We want to add it at the very end. So the way we'll do that is, well, does anyone, based on what we've said, does anyone have an idea for how we would do that? Like, let's say we're in this section where we know that self.next, yeah.
You just do a, you know, while there is a next thing, just keep going through it. And then when you find that there isn't a next thing, then you assign the new.
Okay, so but what are we going to put in here? What's the actual?
Well, kind of like what you did before, you're going to have to set, so while self.next, I guess.
Well, the problem with that is that self.next, self right now points to the head of the linked list.
Yeah. So you're going to want to do the current thing again, right?
Exactly right. So we're going to say something like current equals self, and then while.
And then while current.
Well, yeah, going to think about this one for a second. So we already have our new thing. We actually we don't want to. Yeah, I think here we actually do want to say while current dot next, because as long as there's a next, we'll keep going, but we don't want to, we want to stop when we hit the current who's next. You know, do you see what I'm saying? Like right. So our current is going to point to, let's say, this element right now, this 4. And then we'll say while current dot next, well, current does have a next, which points to this 12. We just want to get to that last one as quickly as we can. So we'll say
just
while
keep
current
reassigning current. Yeah, keep reassigning current.
Right, while current dot next, then current equals current dot next. So this is going to run once, and now current is going to point here. And then that itself has a next, so we're going to run it again, and now current points here. And now current points to this 6, but this 6 doesn't have a next. So we know we're done at that point. And now we can say current dot next equals that new node.
You can also take out 9 and 10.
Exactly. Yes. We're going to get to that in a second, but I just wanted to show that to show how oftentimes you will build something up incrementally. So, so we have everything we need now, as long as this prints 6. Whoa, it didn't. See, that's a good point. What did we do wrong? What did we do wrong? First, can we take this out and it still works? No, we definitely messed up at some point. I don't remember messing up, but well, let's try that first way. That works. So, okay, so in our first case, we say if self.next, which is our first thing, is, or if self.next is none, or if it is none. I like things to be readable, so I can't even read that right now. Might as well. If self.next is none, then set self.next to the new node, and that's going to work for 4. And then importantly, we should probably return at that point. And then I'm going to say otherwise, if self.next was not none, then I set current to self, and while current.next has something, I'll reset current to current.next. And then when that's done, I can set current.next to that new node I created. So does this work now? We'll see. Okay, that seems to work. I'm not. And then does this work? This works, yeah. So as I think Daniel was saying a second ago, it looks like we can make this a little better, because I originally wrote it in such a way as to say, like, well, you know, adding the first one is going to be kind of a special case scenario, and then I'll worry about adding the rest, because it did seem like adding the first one was simpler. But as it turns out, it doesn't really matter, that I could just say something like, the first thing I do is say current equals self. And then once I say current equals self, I can use this to say, go all the way to the end. So if, current equals the first one and dot next is none, this doesn't happen. But if there is a next, then we keep reassigning it until we arrive at the only element with something in it. And then finally, when we hit that, we can just say current dot next equals linked list value, and then we don't even have to ever create a new node variable. And this should do everything we want. Let's just make sure it does. Yep, still working. And so this now works. This lets us append to a linked list, and all other problems we can try and do would be something like, some other things you would want to do with a list-like thing, where we say, okay, well, we want to insert at a specific point, or we want to delete at a specific point. Or maybe we want to have something like pop, where, append is sort of like push, where it's pushing it at the end. What if we want to just always get the last thing we put on right off? And then you could start asking yourself, well, is this even the right data structure for that, if we're going to be doing that a lot? But something to mention is that we had this little debate earlier about like whether it made more sense to have a node or not, whether just like a linked list is the first node or something else. Well, I think the only downside to doing it this way is that, let's say we create a linked list, but the way we're doing it, a linked list must always seemingly have at least one element in it. Whereas what if we wanted it so that a linked list had nothing in it, and then we added things to it, but then we could also delete things from it, including that very first node. So in that case, you might want some separation where you say like a linked list is a head that could be none or could point to that first node.
Yes, see, that makes sense. And I think maybe I asked my question poorly before. I just wanted to know what the point was, because I didn't see it, but what you just said makes total sense of like why you'd want.
Yeah, and I would say like all the ways you can define a basic data structure, they're all very similar, but there are these choices you can make. And those choices always boil down to some kind of edge case of saying like, well, any way we did it would be fine most of the time, but what if we have this situation where we just like want to make sure that we can delete everything, or alternatively, sometimes making a specific design choice can make it so that an algorithm like this runs better. So you want to make sure that there's as few special cases as possible. And maybe I think the way we're doing it right now is in part simpler, because we assume, instead of saying linked list.head at any point, we're saying, okay, well, we always know we're looking at a node, and a node has a next, and that just is sort of like a nice structure that makes it simple to walk through. There's no special case of first node. Okay, but that's all I really wanted to get through with the linked list. And there's a problem we could do, which I think we should probably give you guys a break and then come back to do that lead code problem. But I'll give you a taste. It's right here. I guess I could share that in the chat. And I have a solution, but we can do it collectively. And right, we're going to take, well, first we'll take some questions, and then we'll take, how about a 15-minute break? That sounds about right. And then we'll do this linked list problem, which I don't know, you guys shouldn't see my answers, so maybe I was hoping I could, when you guys click that link, do you see my answers or no? No, okay, good, yeah. So we just want you guys to have the leak code problem. And I wanted to show it to you guys because I don't want to intimidate you too much, but it is a good, leak code calls this, it calls it a medium problem. Okay, that is reasonable. But basically, most of the time on these interview things, it's almost like they're not just saying make a linked list, rather solve a problem that by the nature of that problem forces you to show that you know what a linked list is. It often feels arbitrary. So we'll see for example, in this case, seems very odd. We have two numbers represented by linked lists, and then we want to add them together. but the link list 243 represents the number 342. 564 represents the number 465. And then ultimately we want to return the link list 708, which represents their sub 807. So that seems backwards. That seems weird. Why are they doing it like that? Mostly just because it's a contrived problem to show that you understand this idea. But we'll do that when we get back. For now, let's just do any questions we have and then break. Okay, well, if you don't have any questions, you can go on break. But just sort of as a group, we're hoping we can get some kind of poll where people either say like yes mustache, no mustache. So
No,
we're all about feedback here. This isn't about me, this is about you. So we just want to get this exactly right on the facial hair that will make the class gel. But you have 15 minutes to think about it. I see
All
Dan
right.
to answer. But Dan,
Yen had her kid sitting on her lap earlier, so I don't know if a mustache is allowed in that case.
yeah, honestly, it is true that anyone who's ever worn a mustache in public knows that you got to be on your best behavior. Like if you smile at a kid in the supermarket, people don't like that. You can't you gotta be careful when you're wearing a mustache. Okay, cool. Yeah, see you guys in 15 minutes. Oh, Zainab, should we have been recording this?